Hello, everyone, and welcome to today's lectures on classical machine learning. I hope that you enjoyed the previous days covering the basics of quantum computing, giving you an idea of how to think about quantum circuits and objects in quantum computation, as well as the pitfalls of noise and the near-term devices that we have. So today, what I want to take you through is really the basics of classical machine learning. My name is Amira, and I'm a researcher, part of the IBM team, and I focus specifically on quantum machine learning. And if we want to hope to understand quantum machine learning, well, we have to cover the basics of classical machine learning. And so today's lectures, I'm going to cover the terminology that is used often in machine learning, like models and data and cost functions, exactly what these things mean. And then we'll go a little bit deeper into some of the popular models that's used in classical machine learning. So let's begin. Well, what is machine learning, right? So this is a very difficult, I think, question to answer because machine learning has now become this very broad term that people use interchangeably with AI, and I think it has a lot of different definitions. But the field of machine learning, what is so beautiful about it is just exactly how much it incorporates in itself, right? So it draws from statistics, mathematics, all the way to behavioral economics, right? So machine learning really is a multidisciplinary field. And I think if you Google the definition of machine learning, you will come up with lots of different ideas, different thoughts on how to think about it. But I think I like a very simple definition of machine learning. It's really trying to try and get a computer to learn patterns from data, right? So it's really trying to understand underlying structures that exist in data and then use these underlying structures to draw inferences or make conclusions about new information, about future things, and about predictions and stuff like that. And so getting a computer to try and understand these underlying structures and patterns that exist is really the goal of machine learning tasks. And so mathematically, how we can think about this idea is through function approximation and optimization. Now, what does that mean? Well, it means that we can assume in nature that there exists some true function or relationship or set of rules that allow us to interpret inputs in a certain way. So, for example, let's say that there is some true relationship that we can write by G, and G takes in some inputs X. Now, this could mean that maybe G takes in, for example, X is pictures, images. And so what this means is that there's some true underlying structure in these images, in the data that is provided. Now, for example, we as humans can immediately identify these structures quite easily. If I show you a whole bunch of pictures of cats, it doesn't matter where the cat is in the picture, what color the cat is, we can identify that as a cat. Now, for a machine learning model, this is not such an easy task. And so it has to kind of learn from information and data in a sequential manner or in a meaningful way, such that it can start to do these human-like tasks, like identify pictures of cats when we feed it new images. So in reality, we don't know what this true function G is, right? I mean, I said as humans, we are good at doing this stuff, but mathematically, how do we write down this actual true relationship that exists? And so in machine learning, what we try to do is we try to approximate this function G with a mathematical model. So I'll call this mathematical model F. And this model will take in some subset of the data. So I'll just denote that by X bar, because we very often don't have all the data available to us in the world, right? We don't have every single picture of a cat ever taken. So, so we approximate the true function G by taking in some data, some subsets of the true population of all data. And importantly, crucially, this function F is parameterized, meaning that it depends on some parameters theta, and these parameters are the things that we try to tweak and change and optimize such that we get the best approximation to the true relationship that exists, which is this true function G that I call. So the whole goal of machine learning is really to find this optimal set of parameters, theta, for your model. And as a machine learning engineer, you also have to basically kind of design and pick this model in the best way. And so there are lots of different models that exist that we can choose from. You will go through some of those in the next lecture. But as a machine learning engineer, your tasks are really two things. It's how do I choose my model? And then after I've chosen my model, well, then how do I get the best parameters that approximate the true function g as closely as possible? And so this is very broadly the framework for all machine learning tasks. Okay, so now we can go through some machine learning ingredients, right? So what are the things we actually need to accomplish this task of function approximation and optimization? So let's start with the first ingredient. The first ingredient, which I'm sure you guys will have already guessed, is the most crucial thing. It's data, right? So getting a machine learning model to learn structures and patterns, we have to feed it data. We have to give it information relevant for the task that it's trying to complete. So let's say, for example, that the task is for a machine learning model to classify what's in an image. Now, how would a machine learning model even understand what's in an image, right? Or let's say in a video or anything like that. And so data itself has many different forms. And this is something that's really important to understand, that there are different types of data, and depending on our model, we have to feed it appropriate data for our task. And the data type will also affect the type of model that we choose. So let's say that we start with pictures, right? And now, how does a computer process or understand what a picture is? This also took me a while to figure out. I was always wondering, like, how, people just talk about, we throw lots and lots of images into a computer, and then the model trains. Now, how does it process images? So let's take a very simple example of a picture with a flower. And I am a terrible artist, so please excuse my drawings. But let's just say, yeah, this picture has some flower in it. And now how would we feed this data point into a computer? Well, every picture has these tiny little pixels, right? They can be broken up into pixel values. And these values of these pixels can be written as numbers, right? So where, for example, the pixel values can lie between, let's say, -1 and 1. And the lower the pixel value is, then the darker that pixel is. And the higher the pixel value is, and that means that that pixel is lighter, right? And so, of course, the pixels in the image will have different numerical values that depend on how dark or light those pixels are. And so let's say this image of a flower is a 28 by 28 pixel image. So that means that there are, if my math serves me correctly, 784 pixels in this image. So we can write a data point for this image as, I'm going to call it x1, and we can represent this data point as a vector. And this vector will contain all the pixel values that is in this image, right? So it will contain all kind of 784 values. So let's just say the first pixel value is like 0.8, the second is 0.2, all the way down to the last 784th pixel entry, which is, let's just say, -0.5. And so this is how we can kind of represent an image as a data point, right? So this is one data point, one image that is represented in a vector as a vector notation. And how many entries the data point has in this vector, this is referred to as the features of the data. So this is another important term that we'll need later to understand machine learning data and models. And so this is the features of the data. So every data point can be represented as a vector, sometimes even other objects, but let's just think of them as vectors for now. And the entries, the number of entries in the vector determines the number of features of the data. And so this is also sometimes referred to as the dimension of the data. So you'll hear people say the size of the data, the dimension of the data, and this typically refers to how many features are in the data. Okay, And then we can kind of write our full data set, right? Let's just say we've got some full data set that exists, and we can write it then as all of the vectors, right? So like, let's say we've got n samples of data, then we can represent our full data set as like all these vectors, right? So there's n samples. So that in this case would mean that we have n pictures of different flowers, for example. Okay, and sometimes, just for completeness, I want to say that sometimes people represent the full data set as a giant matrix, right? So you can also think of like, let's say this X full, like the full entire data set, can be written as this giant matrix where you can think of each column in the matrix as a data point, right? So this is, say, X1, X2, all the way to Xn, and we'll have here the features of each data point, right? And so there will be, in this example, 784 data points, and typically this is generally just referred to as D. D, the number of features in your data. Okay, so this is data, the first ingredient. Then the next ingredient, which you, of course, would have guessed as well, is now we need to understand the model, a concept of a model. And a model, very simply, just kind of takes data, let's just say we have some data, and we pass this data into a model, which is simply some function or mapping that takes in this data, depends on some parameters, which we mentioned earlier, and then gives us some output or prediction. So we normally refer to this as y hat because it's an output, a prediction, a label. Let's actually write that down. So we can refer to the output of a machine learning model as a prediction, or sometimes we call it a label, or just like an output. And sometimes it could even be a distribution. And we can write it as y hat, or we can just even write it as simply the function itself, right? That takes in a particular data point, depends on some parameters theta, and we can write it like such. And now these thetas, these parameters, I like to just refer to them as a set of parameters. I don't want to write it as a vector because it's not always a vector. Depending on your model, it can be a matrix, it can be other objects as well. So I like to think of these thetas as sets of parameters, and their dimensionality will really depend, or their structure will really depend on the type of model that you choose. So we'll get into exactly what these thetas can look like. And these are the things, of course, that we want to solve for and find in our model. Okay, so I also didn't really mention exactly what this F is, right? And so we'll get to that in the next lecture, but you can think of F as a linear model, a neural network, support vector machine, and all these ideas that we are familiar with. Okay, so next, once we have a model and we've passed it some data, and we can compute the predictions, the outputs, the labels, well then how do we actually score our model? How do we know that our model is good, right? And so this is exactly the idea of something called a cost function. A cost function wants to take our model's predictions and score them in such a way that you know how good your model is performing. So we typically write our cost function, let's say as some function C, and this function takes in my model outputs, right? So let's just say it takes in my model predictions, which I can write as this function F, and it compares my model's predictions to the correct predictions if they are available to us. So for example, in the task of classifying pictures of cats, my model will produce a prediction whether there's a cat or not, and then we can score the model based on the cost function. The cost function will compare it to the true value, the true label. In fact, there is a cat, and then we can get an understanding of how good our model is performing. So remember I said that this is sometimes referred to as y hat, the prediction, and then the correct or the true value is simply referred to as y. And so this cost function here really gives us an idea of how to score our model appropriately. And so when our model is wrong, we often want to penalize our model, right? So we want the cost to be very high when our model makes mistakes and the cost to be very low when our model is correct. And so an example of how to think about a cost function is something called the mean square error. The mean square error is simply defined as the difference between my model's prediction and the true output squared. Now, let's say, for example, that the task is simply classifying cats again, right? So if, for example, like if there is a cat in the picture, so let's say there's a cat, then my model will output 1. If there is no cat, let's say my model outputs 0. So let's say I feed an image to a model, and my model says that there is a cat in there. So it gives me an answer of 1. But the true solution is that there isn't a cat. So the true solution is 0. And so this would give me a cost of 1. Whereas if the model was correct in classifying the data point, then it would be 0 minus 0 squared, which gives me a cost of 0. So this is an idea of a simple cost function that scores your model appropriately when your model makes mistakes and when your model is correct. And so the higher the cost, the worse your model is classifying your data, the worse your model is performing on the task at hand. Okay, cool. So now we can look at some machine learning examples. So we've covered the basics of the ingredients, the data, the model, scoring your model. Now let's look at some examples in practice. So the first example that I want to mention is this idea of classification, right? So we've already spoken about classification of cats and dogs and pictures, but I think one of the best or the oldest example was really classifying, for example, emails as spam or not. And so a machine learning model, for example, can be trained to look at historical data, so lots and lots of previous emails that have been marked as spam or not, maybe manually by a human, and then learn patterns from these emails to mark future emails as spam or not. So maybe, for example, the machine learning model learns that emails with the words money and urgent and help kind of most likely or are more probable to be marked as spam. And so these are the types of structures that exist in data that machine learning models can learn. Another example, of course, is image recognition, which we spoke about. And a very famous data set here is called the MNIST data set, which is simply a data set of people's handwriting where they write digits. And so the task for a machine learning model is to classify correctly based on someone's handwritten digit, whether that is what that digit is in real life, right? So this is actually wasn't so easy initially for a machine learning model to do because everybody's writing is different, right? So how I write a 0 and 1 could be very different to how you write a 0 and 1. So the machine learning model has to generalize and like kind of understand a general distribution of pixels for certain numbers and learn how to classify them correctly. Then there is, of course, the age-old example of regression. And regression, you will know if you've taken any statistics course, can also be thought of as a machine learning model, actually. Regression tasks typically try to learn from historical and relevant data to try and make predictions, numerical predictions, about a future event. And so, for example, in this picture here, I have the weather forecasting. So weather forecasting, let's say for the next week, could be used with a regression model where you could take the historical weather for, let's say, the last 50 years and use that in your model to inform how to predict or to forecast the next day's weather. Then there is clustering. Clustering, I think, is really, really cool because there are so many different applications that you can use. And also this is the machine learning models in here are very, very beautiful. So clustering models try to take lots and lots of data. Let's say, for example, about individual consumer behavior. Let's say that we have all the data for how different people purchase food and products. If we have this information, then we can start to group individuals together. Let's say that this cluster over here, for example, consists of people who buy milk, and people who buy milk typically also buy bread. But then this cluster over here, for example, has a very different buying profile. Maybe they buy a lot of luxuries, they buy a lot of sweets and chocolates and so on, and they're less likely to buy healthy products. And let's say, for example, this cluster here has different consumer behaviors, right? Where they are, I don't know, vegetarians, and so they never buy meat, and they're more likely to buy vegetables and healthier things, for example. I mean, a very trivial, naive example. But why this is cool is because you can start to cluster or group people or individuals together that have similar behaviors. And now, as a company, if you want to do, for example, targeted marketing, this is really helpful because you don't want to market or sell sweets and unhealthy products, for example, to the people who are only interested in healthy things, right? Because then you're not achieving your target marketing appropriately. I mean, there's a much more efficient way to do that. You want to market the product to people that are most likely to buy that product. And so this is quite interesting, and this has also become a really popular a popular task in social media and social networking, where companies are trying to group individuals based on their different spending patterns or behaviors and try to offer them really tailored marketing products that they would be interested in. Then the last example that I want to make mention of is machine learning tasks where the task is to generate new data. And now this was a major breakthrough in the last couple of years where machine learning models could learn and understand patterns from historical data and then produce entirely new data. And this was just so beautiful. So what you're looking at here are images of faces of people, but these people do not exist in real life. These images have been created by machine learning models that generate distributions of pixels that can very closely mimic real life pictures of people. Now, how did it do that? Well, we fed in tons and tons of pictures of all kinds of faces, of all kinds of people, and then the machine learning model, it did exactly the task that we mentioned, right? It kind of learned and understood structures that exist that underlying the data. And so this was really quite amazing. These pictures are generated by a model called a GAN, a generative adversarial network, and you will hear about this later on in the courses as well. Okay, so now let's go back to function approximation and optimization and thinking about our machine learning model mathematically. And so let's look at a specific setting. So in machine learning, there are kind of three groups, I would say, or three settings that we can operate in and think about. The first is this idea of a supervised setting. And now a supervised setting quite simply means that we have the labels or the outputs, the true labels, the true outputs of our data. So in the case of pictures of, let's say, cats and dogs, when we feed into a model a picture of a cat or a dog, we know that its true label is assigned to it. So we know what the true label is. So if we had to write that down mathematically, well, we can say that we have some data. Let's change the color. We have some data, let's say one data point, and we know its true label, which I call Y1. And so in general, we'll have lots of data points, let's say n samples, and we will have the labels associated with them. So this is the crucial distinction of a supervised machine learning task, where we will have, for example, let's say our first picture is the cat. Again, my artwork, terrible. And then we have we can represent this, remember, as long vector containing the pixel values. And then our y can be, for example, let's say if it is a cat, then the label is 1. If it's a dog, then the label is -1. And so in this case, where we have this data point, x1, then our label is a cat, so it's 1. And then the opposite is true for a picture of a dog, right? So we can start to create these sample pairs of data points with labels in a supervised setting. Okay, so then what is the next setting? The next setting that we can look at, as you might have intuitively guessed, is an unsupervised one. And now in an unsupervised one, quite easily, we can just understand that we don't have the labels of the data. So if we don't have the labels of the data, how do we kind of optimize our model, right? This is not an easy task. In fact, an unsupervised learning setting is arguably a lot more difficult. But remember I mentioned to you earlier that there exists some true relationship, some true function in nature that we want to approximate. And so in this unsupervised setting, we just try to choose a model, some data, we just try to choose a model that as closely as possible mimics the true distribution or the true function that exists in nature. So in the example of when we mentioned about GANs that generate these pictures of people, then this is exactly an unsupervised setting where we feed into a machine learning model tons of images of real people. And the idea is for the model to pick up underlying structures that exist that we don't necessarily know or have the labels of, and then reproduce these structures such that these structures make sense in nature and they actually correspond to real things. So this is the idea of an unsupervised setting where you don't have the labels of your data. And then lastly, I want to make mention of reinforcement learning. So reinforcement learning is a really, really beautiful subfield, I guess, in machine learning, and incorporates all kinds of things like models, training models, and it can get very, very complicated. So I want to just give you the intuition, the idea, the high-level overview of what reinforcement learning is, so that when you hear it later, you will know the basics of what it's about. So reinforcement learning assumes that we start with, it's a totally different idea and setting. It assumes that we start with something called an agent. And now an agent you can think of, let's say quite simply, as a character in a game, let's say a character in a video game. Let's say you are this little person here. And in this video game, you know how to program the rules of what you can do, right? So let's say in this case, this little character can either move forward, it can move left or right. And now it needs to kind of navigate to achieve some sort of task. And how it navigates is it navigates through something called the environment. And so it can compute or it can execute different actions, right? So if you are this player in this game, you know that the actions that you can take is to move forward, left, or right. So the agent interacts with the environment through some actions. Now, the whole idea is to choose the best actions to navigate through this environment. But how do you know what actions are good or not? And so typically, there is a task in the game or in the setting, the reinforcement learning setting, that says, okay, let's try to achieve some goal. Maybe the goal is to get to this apple. And on the other side, the little character could also fall into, let's say, a river and drown. And so there is this idea of scoring based on the different actions that you can have in the environment. So if the agent achieves the task of getting to the apple, it could get a score of, let's say, +10. But if it falls into the river and makes the wrong moves, then it gets a score of -10 and the game terminates. And so now the machine learning task or the optimization task is to really figure out how to navigate, how to act in the environment such that you maximize these rewards. So for every action that we take, we get a reward, and this is fed back into the agent, and then the agent makes another action. And so the idea in this whole setting is to really figure out the optimal actions that maximize the rewards. And so this is the idea of reinforcement learning. It's an agent interacting with an environment, and it knows the rules of the environment, and it now has to figure out how do I navigate through this environment to maximize my rewards. And reinforcement learning has spurred a whole bunch of beautiful machine learning success stories. And in fact, it is really, really good at playing very, very complicated games. So what you're looking at here in this first picture is the game of Go. And if you haven't watched AlphaGo, the documentary, I highly recommend watching it. It's a beautiful story. about how they use reinforcement learning to train models that can actually perform better than the world champions. And so in the game of Go, a reinforcement learning model was able to beat the champion in Go, the world champion. And the number of configurations in this game of Go is greater than the number of atoms in the observable universe. So this is really quite an impressive feat because reinforcement learning, very importantly, does not brute force search over all possible combinations of moves and then figure out how to optimize over that. That's just almost impossible. It's instead kind of learns patterns and tries to understand how to optimally play the game. And so then this also then created opportunities for reinforcement learning models to play other games. So StarCraft, for example, and Dota were also trained, like people were trained, I should say models were trained to play the champions in the world. And these models performed very, very well and actually beat the world champions in Dota and StarCraft as well. So I recommend like checking out the videos on that and watching the people play live. It's really, really impressive because these games are not easy. They involve a lot of skill, a lot of thinking, a lot of human-like behavior. And so for machine learning models to actually beat humans in these tasks is really quite impressive. All right, so now let's talk about a specific kind of setting, right? So we discussed supervised, unsupervised, and reinforcement learning. Let's focus on the case of supervised. And in particular, let's look at a specific type of task, right? So let's say that we want to classify the type of flower based on certain features that exist in the data. So as an example, okay, so the first ingredient we know, we must always start with data, right? So let's say in this example, this concrete example, that we have lots of pictures, or let's say not pictures, let's say lots of information about our flowers. And we have that the flowers can either be roses. Let's change the color. The flowers can either be roses or daisies. And so our labels then can be either a rose or a daisy, right? And let's say we map these to class +1, class -1, as a very trivial example. And now let's say that our data that we have for each kind of flower that we have available to us looks something like a vector that contains, let's say, the length of the flower's petals and let's say the width of the flower's bud, as an example. So this means that the number of features that we have here, the dimension of our data, D, is equal to 2, right? So the number of features is 2. And let's say we look at a specific data point. So we'll have x1, and let's say x1 has a length of a petal equal to, I don't know, 0.8 centimeters, and the width of its bud, for example, is 0.1. And this specific label is +1, meaning it is a rose, right? So this is an idea of how we can think of a data set. And now what is typically done in machine learning, and this is quite important, is the full data set is divided into 2 sets. So if we have, let's say, the full data set, what is typically done is, and let's say this full data set has 120 samples. So we have 120 vectors that have the length and the width of the petals and the buds, as well as their labels. So what is typically done is this data set is split into 2 groups. It's split into a training data set and a test data set. So let's say that we split our training into, let's say we take 100 samples here and we leave the 20 for the test set. Now, why do we do this? Well, we need a way to evaluate our model once we've kind of trained it or optimized it relative to our data set. So for example, if we create a model and we feed in 100 samples of our flowers, and we optimize relative to these 100 samples, how would we know how to check its behavior or its performance on new samples? And this is why we hold out some samples and call it a test set, because it's a way to assess our model on new data, on new information. So we don't train our model on these test samples. We keep those test samples so that we can score our model once we've optimized it on the training samples. Okay, so now that we understand our data, what kind of models can we have? So I told you earlier that we write like our model F, which takes in a data point, depends on some parameters, and gives us some output or label or prediction. And in our example, our features, D, set number of features, is equal to 2, right? So remember we had our vectors, and this had the length and the width of the petal and the bud. So now as a model, we can kind of pick something, right? So let's say we pick something very, very trivial, like a linear model. And in the next lecture, we'll discuss in more detail different types of models. But let's say we choose a linear model. Then we can write our linear model as this prediction that comes out of theta times our data point, and I'm just going to ignore biases for now. So let's just say that it's theta times our data point. And now remember, our data point is a vector with 2 entries. So theta in this sense also needs to be a vector, and it needs to be a transposed vector so that this equation can make sense. So in this example, we can write theta as a 2-dimensional vector, transpose, say theta 1, theta 2, times by x, right? And x, let's just say, I'm going to say has feature value x1, feature value x2. And then this will give us a scalar output when we multiply this out. You multiply this out, remember it's row times column, so we'll have theta 1 x1 plus theta 2 x2. And these x's, remember, are not data points now, they're just our feature values, right? So we can have lots of different data points that get plugged into this equation, into our model, and give us predictions and answers. So now the whole idea is to then, so once we get our, let's say our y hat out of here, we need to compare these y hats to the true values. And then we can work out on picking the best possible thetas that kind of minimize our cost value, which remember what we talked about earlier, cost, that minimize our cost relative to our objective of correctly classifying roses and daisies. So what am I trying to say? I'm trying to say that we have a model. Let's just erase all of this for now. We have a model here. And in this model, we can plug in all our data points. We can plug in our pairs of x1, y1, x2, y2. We can plug in all our data and then check the predictions against the true labels. So this is the idea, and we have to remember, importantly, plug in the training data. So we plug in the training data and we can get predictions. But how do we choose this theta? And that is the entire goal of machine learning, right? We need to pick a theta, a set of parameters, such that the cost is low across all our data points. So let's define what a cost function can look like. So in our case of our 100 training samples, let's say for our 100 samples, training samples, let's define the cost as the mean square error again. But now, since we have multiple samples, we can take the average of the mean square error as our cost function. So we can define our cost function as the average of the sum over our training samples, our 100 training samples, And every prediction that we get for each data input minus its true label squared. And so this gives us an idea of how our model is performing over all the training data points. And this is the thing that we want to minimize. We want to minimize this cost because we want our model to make the closest or the truest predictions to the true label, right? So we want it to be as close to the true labels as possible. So how do we minimize this cost, right? How do we do that? How do we pick a theta? Let's just say, how do we pick this set of theta such that for every training point that I have, the label is as close to the true label as possible? And so this is what picking this theta is exactly what people talk about when they say they are training the model. It means they are optimizing and figuring out how to choose these theta sets, these parameters, such that we minimize the cost value over our training data, over all our data points that we have to train our model. Okay, so how do we do that, right? I spoke to you about just kind of this idea of having an optimal theta set, but how do we actually pick the thetas? And so this is really, really quite a beautiful idea. Let's say that, that we have our cost function and we can plot it in 2 dimensions, right? So what you're looking at here on the y-axis is the cost. This is the thing that we want to minimize. And on the x-axis, we have all the possible sets of parameters that we can choose from. So I just denoted it as a vector, but doesn't necessarily have to be, right? But let's just, for a simple example, say that these are the different parameter sets on the x-axis. So this here would give me some set of thetas, maybe, I don't know, equal to 0.1 in our 2-dimensional example, 0.8. This would give me another theta that's maybe equal to 0.5 and 2, just as an example, right? So how do we go about choosing visually in this example? It's very easy to see that whatever the theta is here, this will give us the minimum cost value. But in reality, how do we go about choosing that? And so this is where an algorithm called gradient descent comes into play. Gradient descent is a beautiful, beautiful algorithm that says that, let's say we choose some random values for our parameters, some random initialization. And let's say that we pick that random theta over here. So I'm going to call it theta 1. Then we know that our cost at theta 1 is equal to this thing here, this value here, and it's quite high, right? So gradient descent says to us, let's calculate the gradient, the derivative of the cost function with respect to the parameters that we initialize at. So with respect to theta 1 in this example. And what this will give us is a gradient vector. This will give us a gradient vector tangent to this cost value here. And now the whole beauty of gradient descent is it says, well then let's update our parameters. So we initially chose theta 1. Let's update our parameters, and how we do that is we update them in the opposite direction of the gradient. So we get a gradient vector, this pink line, and then we figure out how to change our parameters and update them such that we descend down the gradient. We move down in the opposite direction of the gradient. And so then when we pick our next thetas, we kind of choose them in this direction. And so now let's say we pick a theta here. I'm going to call that theta 2. And then we do exactly the same thing. We go and we calculate the gradient with respect to this theta 2, which will give us a vector in that direction. And then we descend and we update our parameters in the opposite direction. And you can see from this picture that eventually we'll pick the theta star that gives us the minimum of the cost value. So this is the idea of optimizing your model and training your parameters. And it involves a very, very simple idea, right? It's just computing mathematically the derivative of your cost function with respect to your parameters, and then updating your parameters using this gradient information. And so how gradient descent is written down or formulated is typically like this, where you have your update rule, you update your parameters in the next step by using your initial parameters and then descending down the gradient, right? So here is the gradient of the cost function with respect to the parameter set. And then this eta value over here is something called the learning rate. So this tells us how big a step we want to take in the opposite direction of the gradient. All right, so now we've covered the idea of gradient descent, and you might then also think, okay, but what if I initialized my parameters here? Let's say this was the theta one we started with. Then we would get our gradient vector that goes in this direction, and our update rule will tell us to change our parameters in this direction. And then eventually we would converge to a parameter set here. And this is clearly not the global minimum of the cost function, right? The global minimum lies here. And so now what happens in this gradient update rule is we get stuck in something called a local minima. A local minimum, or I should say minimum. And in reality, this is actually a huge problem because cost functions don't look so simple like I just drew them now. They are actually a lot more complicated, right? So now you're looking at a picture here of a cost landscape of a neural network. And this is super non-trivial, right? We can see, okay, here is the global minimum, but look at all these tiny minima that lots and lots of local minima that our model can get stuck in. And so in reality, these cost function landscapes are extremely complicated. And so how people try to combat this is by using something called stochastic gradient descent, which means simply that instead of calculating the derivative of our cost function using all the data available to us, all the training data, we just sample at random subsets of our training data. And I don't want to spend too much time on this, but what I want to make mention of is that this stochasticity actually has been shown in practice to work very well to escape these local minima that you could end up in when training your model. So this is a very nice, finding and a nice algorithm. Okay, so let's just recap training the model. Remember that we have some training data, so this is some subset of our data, right? And so in our example, we had 100 of them. And then we take this data, and the next step is to plug it into our model. And our model will give us lots of predictions for our data points. We take those predictions and we plug them into a cost function to check how well our model is doing. So we compare y hat to the actual labels in the supervised setting because we have them. And then we can figure out a cost or a score for our model. And we usually randomly just start by picking some random parameter set theta. So we pick theta at random initially. And then to find a better theta to lower our cost value, then we compute the gradients of our cost value. We compute the gradients with respect to our initial theta that we pick. And then using that gradient information, we can figure out how to update our thetas, plug that back into our model, that hopefully lowers our cost value. And we do this over and over again, and this is training the model. We train it until we are happy with the final cost value that we achieve. Now, after we train the model, we have to assess our model, right? And so this is exactly where the idea of holding out the test data comes in. So then if you remember, we kept 20 data points, so 101, 101 all the way to x 120. So the last 20 samples were test data points that we held out. So our model has never seen these data points before. So then we take that data and we plug it into now our optimized model, right? So now we have kind of this theta star that we've trained through that iterative cost function optimization process. And so this optimized model will now give us predictions, 101, for our test samples. And then we take those predictions, and again, we can plug it into a cost function and just check how did our model perform and do. And if our model is good and it's optimized in an efficient way, and it's able to actually learn the true nature of the task, then we would expect our cost to be low on the new data, on the test data that the model hasn't been trained on. And so this idea of minimizing the cost on new data, on new information, on data that hasn't been used for training, ties into one of the biggest questions of classical machine learning, the biggest problems and questions called generalization. And model generalization is really, really quite beautiful. So in these last 10 minutes, I want to actually just show you what this notion of generalization means. So generalization is simply trying to answer the question of how well will your model perform on unseen data, on new information. And so a proxy for that in practice is using a test set and checking how your model will perform on a test set, right? So in the case of our roses and daisies example, let's say that we can actually draw our data because it's in 2 dimensions, right? So we've got, for example, on the y-axis, the size of the bud, and on the x-axis, we've got the size of the petals. And now let's say that our roses kind of belong to a group of, so each X here is a rose that I'm drawing. And these roses kind of seem to have shorter petals and bigger bud sizes. Whereas for the daisies, the opposite is true, right? Where they seem to have smaller buds and larger petals. Just as a naive example. Okay, and now let's say that we have a test set that we keep, right? So these are some, so each little X, each little dot here that you're looking at is a different data point. And now we can plot our test data. So this is the training data. Training. And we can plot our test data, which is usually a smaller subset. And let's say that it looks something like this. And we've got two daisies as well. Now, the whole idea of picking a model that generalizes well is to come up with some decision boundary, some model that kind of can generalize well on new data. So it doesn't overfit and it doesn't underfit. And I'll explain what overfitting and underfitting is. But we want to come up with some decision boundary, let's say some line that lies here, that tells us everything to this side is a rose and everything to this side is a daisy. So that when we use this model on the test data, it correctly classifies everything. Okay, but in reality, this is not always so easy to do. So while we have this kind of picture here, let me just copy this. There are problems that arise when we think about generalization. So again, let me just remind you that this is just the idea of trying to understand how well a model will perform on unseen data. So if we use training data like these, how well will it perform on new information? So data that it's never seen before. And I just drew the image just now of this idea of having training and test data, right? And now the problems that can arise, or how we need to think about how to create models that generalize well, is through this picture of capacity. So the capacity of a model basically means how powerful is my model? How many functions can my model express? And the more and more functions that your model can express, the more intricate relationships in data it can capture. But having a high capacity is not always a good thing. This is something we will come back to in the last lecture. Let me explain why. The reason is through something called the bias variance trade-off. As we start to increase the capacity of our model more and more, meaning we allow our model to be able to fit more and more and more complicated functions, well, then the variance that our model has on new data, on new information, will start to increase. What that means is that our model will start to overfit our training data set. Therefore, it won't perform well on new information, on the test data. So if we go back to this picture here, what this means is when we have a model with super high variance, then it could look something like this. Now, if this is our model, if we look at it, how it will perform on the training data, on the test data, well, clearly it will misclassify, it will misclassify this data point, right? Because everything to the right of this boundary says that it's a daisy, whereas this is a rose. And so the decision boundary for a very complicated model, a model with a high capacity, doesn't have to look like so simple anymore, like this blue line, this linear classifier. It could be something super complicated that just completely overfits the data. It's too many wiggles, right? It just wants to perfectly classify the training data. But then when you look at it on the test data performance, it misclassifies information. It does not generalize well because the model simply overfits. Now, when we go back to this capacity picture, the reverse is also true, where if we pick a model that's too simple, so on this side it's simple, and here we've got like complicated model functions. If we pick a model that's too simple, then it starts to have something called a high bias. And our high bias just kind of means that our model doesn't take into account enough training data to learn true relationships, to learn true structure, which is what we want. So if we draw that picture again, a model with high bias, for example, could just completely kind of ignore our training data and just come up with a simple classification rule like such. Then when we look at the performance on the test data, well, again, this model will misclassify this data point, right? Because everything here is considered a daisy and everything to this side is considered a rose. And so it doesn't perform well on the test data. So the trade-off is this understanding of picking a model with the right capacity, the right ability to express just enough functions that we kind of minimize this bias variance trade-off. And so when we look at the test error, or the generalization error as we call it, then there is this sweet spot, this trade-off of picking this model that does not underfit, meaning it's not too simple, and it doesn't overfit, meaning it's not too complicated and really, really overfitting the training data, so that we get good generalization performance. We get a low generalization error, which means that our model can generalize well on new information. It can classify new data in an efficient way. Okay, so now let us recap. I want to just spend a few minutes just kind of going over what I said, because I know I've introduced a lot of different terms and new information and shown a lot of things at you. And so the first thing that we did was we discussed data, our model, and our cost, right? And so data really can be thought of as these vector objects, and these get passed into some model. You can think of a model as a black box for now that takes in our data, depends on some parameters, and then gives us an output or a prediction. Then our cost simply takes our output, compares it to the true label in a supervised setting, and tells us how good or bad our model is. If our cost is high, then our model is not so great. If our cost is low, then our model is good. Right? And then we can figure out how to kind of move in these parameter space, right? So like, how do we update these parameters such that we pick the best set that minimizes the cost function? And this we learned is through a nice technique called gradient descent. And these gradient-based methods are very helpful to us because we can compute the derivative of our cost function with respect to our parameters and figure out how to move and update our parameters such that we get to global minimums, hopefully. And then we covered some examples in practice of classification, so SPAM, of image classification, of regression, of clustering, and of even generating new data after learning patterns. And lastly, we discussed a very, very important part in machine learning, which is this idea of over and underfitting. And over and underfitting is not an easy thing to do, but hopefully we can design and choose models with these concepts in mind, where we don't want them to overfit our training data so that they don't generalize well, and we also don't want them to be too simple so that they don't work on new information. So we want them to learn real structures that exist and be able to perform well on new unseen information. And then in the next lecture, we will cover finally what it is to pick a model. So we spoke about linear models very briefly, but we can really now start to open this black box of what a model could look like and what this means for our machine learning task. So we've kind of covered data, we've kind of covered the idea of a cost function, and we will discuss a little bit more details about different types of models, in particular neural networks, support vector machines, and how these build off the idea of simple linear models. So with that, thank you very much for listening, and I will see you at the next lecture on classical machine learning. Take care.